All right, so let us begin the first lecture of PH 503, Quantum Mechanics 1. Okay, so in the last brief interaction that we had, I told you basically about the course policies and the grading policies, and also the Google Classroom has been updated with a new document. The document contains whatever we have talked about yesterday, and I've also updated it with the books that you might find useful and things like that. Okay, so I am not too strict on what book you follow. I have certain preferences, and my preferences obviously reflect in the textbooks that I have chosen. But if you find some other textbook more to your taste and you can understand better, please go ahead and follow that textbook. I have no problems with it. But we should all be on the same page as to whatever we are doing. That's all. Okay, so let's begin. Today's lecture will be rather qualitative. Okay, so I'll postpone the mathematical underpinnings of quantum mechanics to the next lecture. Today, I want to motivate certain aspects of quantum mechanics that are very important for you to get a grip on very early. Okay, so this aspect basically has to do with the fact that there are quantum mechanical states and there's a superposition and then there is probability amplitudes and things like that. But most of these concepts, even though they can be very well introduced as abstract notions, it's easier for us to introduce them in the form of a series of thought experiments. Okay, so thought experiments in physics are actually very useful. They help to illustrate the concept without unduly worrying about whether the experiment can actually be performed. Okay, so the thought experiment that we will be introducing today is a series of what are called Stern-Gerlach experiment. The Stern-Gerlach experiment itself is actually a wonderful experiment that was actually performed by two scientists by the name of Otto Stern and Gerlach. So Gerlach experiment. And this experiment was used to establish the notion of spin in quantum mechanics. Now, at the outset, I should tell you that I'm going to be taking certain things for granted in this lecture. Of course, we would be, so I request people not to annotate on the slide. I think there is a way for me to. Okay. So please do not annotate on the slide. Okay. So the Stern-Gerlach experiment itself is actually an experiment that has been performed in the lab. And I will briefly explain what this is, what this experiment is. Some of you might be actually aware of this, in which case it will be a revision. I will not spend too much time on the experiment itself, but what is more important, at least for today's purpose, is what follows this, this experiment. So the Stern-Gerlach experiment was basically done to understand what is electron spin. Okay, so suppose if you have a charged particle that is moving in a magnetic field, you know that the charged particle interacts with the magnetic field, and there is an interaction energy given by a potential, and this potential is given by minus mu dot B. Okay, now mu is called the magnetic moment, as you know, and B is the magnetic field. Okay, now the force that the particle feels obviously is the derivative of this potential. Okay, and assuming that mu is a constant, which it is, force is a negative gradient of the potential minus dV dx or minus del V in 3 dimensions. So force is minus del V in 3 dimensions. So since mu is a constant, and it is a constant as I will show you, this can be written as mu dot del V. Okay, the gradient of the magnetic field. So the force that the particle feels is given by the dot product of the magnetic moment and the gradient of the magnetic field. And this is exactly what I wanted to take for granted, at least for this lecture. The magnetic moment is given by E times mc, where E is the charge of the electron and m is the mass of the electron, times the spin vector s. Okay, the spin is an intrinsically quantum mechanical phenomenon. There is no way to explain the spin angular momentum classically. So in some sense, it is a little bizarre to introduce a lecture on quantum mechanics by telling you the notion of spin, and for this I apologize. But if you simply take the existence of electron spin for granted, this thought experiment that I'm going to describe will illustrate certain nice concepts of quantum mechanics to you. So for now, simply assume that electron has an intrinsic angular momentum, not the orbital angular momentum, not the kind of angular momentum the Earth has as it revolves around the sun or as it rotates about its axis. That is not what we mean by the spin in quantum mechanics. It has some intrinsic angular momentum called the spin angular momentum, and that the mu vector is proportional to the s vector. Okay, so this is something I want you to take for granted, at least for this lecture. Okay, so what did Stern and Gerlach do? They wanted to understand what this spin is. So the way they did the experiment was to allow atoms of silver to interact with a magnetic field. Now notice that the only way these atoms can feel a force is if there is a gradient of the magnetic field. Okay, so if the magnetic field has a gradient, which means I cannot have a homogeneous magnetic field that is a constant. I cannot have a constant magnetic field because the silver particles will not be deflected at all. They will not feel any force. So I need to have a non-constant or an inhomogeneous magnetic field. So the way they set up the experiment is as follows. So first of all, you need to produce atoms of silver. So they took a big oven and they heated up a bunch of silver. Okay, they heated up a bunch of silver, and this oven had actually a small opening. So like this. Okay, so there is silver atoms here. So this is an oven in which silver is being heated up, and they literally evaporate silver, and silver atoms are able to escape through this small orifice. Okay, atoms of silver that escape through this orifice are then sent through an inhomogeneous magnetic field. So the way you set up an inhomogeneous magnetic field is you can have, for example, a north pole of a magnet this way and a very sharp south pole of a magnet oriented this way. Okay, if both are flat, I generate some kind of a magnetic field, but this is one convenient way to set up a inhomogeneous magnetic field. So obviously the magnetic lines of force will not be constants. They will have some change as I move from the top to the bottom or bottom to the top. So this direction I will call the z hat direction, the z direction. Okay, I don't have to call it the z direction. It is just convenient for me to call it the z direction. It could as well be the x or y directions. So obviously, as the silver atoms pass through this inhomogeneous magnetic field, they do feel a force, and this force in this case is given by F equals, since the only change in magnetic field is along the z direction and not along the x or y directions, this force is given by mu z times dBz times dz. Okay, because dBz dz is the component of del B along the z direction, mu z is the component of mu along the z direction. Okay, so what is mu z? Mu z is simply given by E over mc times sz times dBz dz. So this is the force the atoms of silver experience. Now, an atom as such is electrically neutral. So what is this Sz that I'm talking about? This Sz is the spin of the electron. Spin of which electron? Well, the silver has 47 electrons. So the silver is, of course, as all atoms are neutral, so which means there is 47 positively charged particles in the nucleus that compensate for the total electric charge. And 46, the total 46 of these electrons have a net angular momentum of 0. So the total angular momentum of the atom is basically the angular momentum of the outermost electron, which does not have an orbital angular momentum, but does have a spin angular momentum. To understand why it doesn't have an orbital angular momentum, we had to wait till the end of the course. I'll talk about S states and P states and things like that. This electron is in what is called the S state, which has orbital angular momentum 0, but only a spin angular momentum. Okay. So now, as the electrons are passing through, the aim of the experiment was as follows. So depending on what the spin of the electron is, the silver atom should be deflected either this way or this way or this way or this way or this way, right? Obviously, because obviously the silver atoms are going to be deflected, and the deflection is proportional to the spin. And classically, people did not understand what spin was. People really thought that spin could be anything. In other words, mu, the magnetic moment, can be anything. So if you put, so I'll erase part of this. So if you put a screen over here, so classically you would expect that the silver atoms will be deflected in all possible directions. So you will get a spread like this. Okay. There's a bunch of particles over here, bunch of particles over here, bunch of particles over here. It doesn't have to be uniform, but it has to spread all over, right? But it turns out that they did not see this. What they actually saw was that there was only two clumps, not an entire clump, one clump over here and one clump over here. So there is a bunch of atoms that deposited on the screen on the position P, the top, and a bunch of atoms that deposited themselves on the screen at the position D, the bottom. Okay, there was nothing else anywhere else in between. So the idea that the magnetic moment of the electron could be a continuous value. In other words, the spin of the electron could have any continuous value was thus disproved by this experiment. Okay, this was actually a seminal experiment in the history of quantum mechanics that showed you that the spin of the electron is not something that can have 0.1, 0.2, 0.35, 0.877 or whatever it is. It has to have only certain discrete values. What these discrete values are, we know now. Okay, so we know now that the values of the spin angular momentum along any direction, Sx or Sy or Sz, can be only two values. These are minus h bar over 2 and plus h bar over 2. Okay, this quantity h bar is called h over 2 pi. H is called the Planck's constant, as you might know. Okay, sometimes h bar is called the reduced Planck's constant, but we will not be using that terminology in this course. I'll simply call it h bar. Okay, so it turns out that the spin of an electron can only take two values, plus h bar over 2 and minus h bar over 2. In the early days, people called this phenomenon space quantization. Okay, which actually is a lousy term. It seems to indicate that space itself is quantized. We don't use these terms anymore, but in the early days, that's what it was called. It was actually a very surprising yet very beautiful result that told you that in nature, there are certain objects that are quantized, that do not take a continuous spectrum of values, but they actually only have a discrete number with jumps in between. So spin is one such example. This doesn't mean everything is quantized, but there are certain dynamical variables that can be quantized given the situation. Spin is a variable that indeed is quantized. Okay. All right. So this is the Stern-Gerlach experiment, and this proved that the classical way of thinking about things like electron spin were not really right. I cannot really think of electron spin as a small marble rotating continuously. Okay, if there is a small marble rotating on its axis, then of course a spin can take any value. So I cannot think of the electron spin as a top spinning about itself. Okay, so it is radically different. There is no way to actually visualize this. You simply accept it as something that behaves and talks like angular momentum, but doesn't have a classical counterpart. Okay, that is the way in which you can strictly understand spin angular momentum. All right. So this is the Stern-Gerlach experiment. This was already known to people. Now we're going to take this Stern-Gerlach experiment and we are going to construct a thought experiment out of it. Okay. So what we will do is construct sequential Stern-Gerlach experiments. Okay. The point of this is to try and tell you that something very strange emerges once you have a whole bunch of Stern-Gerlach experiments done in a particular fashion. So how am I going to do this? So first of all, notice that I can place these magnets either along the Z direction, X direction, or Y direction. It is completely up to me, right? So if I place it along the Z direction, there will be two clumps corresponding to SZ values, SZ values, plus H bar over 2 or minus H bar over 2. If I place them along the X direction, there will be again two clumps corresponding to Sx equal to H bar over 2 and Sx equal to minus H bar over 2. Similarly, if I do it along the Y direction, I'm going to get two clumps with corresponding to spin values minus H bar over 2 and plus H bar over 2. So all three components of spin can only take two of these values, plus H bar over 2 and minus H bar over 2. Okay. So the first experiment is exactly what I just described to you. So suppose if I have, this whole setup I'm going to reduce to a simple box. Okay, I'm going to put a box like this. Okay, and I'm going to call this box SG Z hat. What does this mean? This means that this box corresponds to this setup with the magnets along with producing an inhomogeneous magnetic field along the Z direction. That is what this notation means. Okay. Now, what is the outcome of this experiment? The outcome of this experiment is that this splits the incoming silver atoms into two beams, one beam over here and one beam over here. And this beam has this is the beam with SZ value plus H bar over 2. And this is the beam with SZ value minus H bar over 2. Okay, I'm going to introduce a very funny looking notation for these two beams. I'm going to call the beam with SZ equal to plus H bar over 2 with the notation. I'm going to write a vertical line and an angular bracket. Okay, and then within this, I'm going to write Z plus. Okay, the beam with SZ equal to plus H bar over 2, I'm going to call, so if I'm going to make this a little bigger, sorry. I'll make this a little bigger, or rather, plus Z. Okay, I'm going to call this beam plus Z, and I'm going to call this beam minus Z. This plus means that this has SZ value plus H bar over 2. Z means that it is the SZ value that this Stern-Gerlach experiment is filtering, not the X or Y. Okay. Now, why I'm using this notation, it can be a little confusing, but don't worry about it. This is a notation that we will be using over and over again. And this notation is due to the physicist Paul Dirac. And I'll introduce this notation in this way of looking at vector spaces in the next page. Okay. For now, simply accept this notation. It's a funny looking notation. It simply means that this beam corresponds to SZ equal to plus H bar over 2. This corresponds to SZ equal to plus H bar over 2. And this corresponds to SZ equal to minus H bar over 2. Okay. This is my experiment number 0. Experiment number 0. Okay. Now I will move on to experiment number 1. Now, before I move on to experiment number 1, are there any questions up till now? Are there any questions or comments? You can unmute yourselves and ask, or you can quickly type it in the chat window. Asking is easier. It will save time. Okay, so I'll assume that everything is clear and I'll move on to the first tweak that we are going to do to this experiment. Okay, what is the first tweak that I'm going to do to this experiment? Well, I'm again going to consider a Stern-Gerlach experiment, okay, along the z direction. And I'm going to get two beams, one with plus z and one with minus z, okay? And I am going to block out the minus z beam, okay? I don't want it any further, so I'm going to put any blocking material that will just absorb all these electrons. And the ones with plus z, so again, this is SG, z direction, this is plus z, and this is minus z, and the minus z beam has been completely blocked. And the plus z beam, I am going to put through another Stern-Gerlach experiment in the z direction. Okay, what am I doing? I'm blocking out the beam that has SZ value minus h bar over 2, and I'm only looking at the beam with the SZ value plus h bar over 2. And along the beam with the SZ value plus h bar over 2, I'm introducing another Stern-Gerlach experiment in the z direction, which means I'm again introducing an inhomogeneous magnetic field along the z direction, and I'm putting a screen and I'm trying to see what I get. Now, somewhat not surprisingly, what you actually get is exactly what you put in. So you get the exact same beam all over again. Okay, nothing new comes out. And you say, what's the big deal about this? This is exactly what you should have gotten, right? Because you're only looking at beam with SZ value plus h bar over 2. So if you put it into a Stern-Gerlach experiment that is supposed to differentiate between the spin values, it cannot, because there is nothing to differentiate. There is only one beam with one particular spin value. So that is the exact same beam you're going to get. Fair enough. So let us make this slightly more complicated. So the second tweak that I'm going to be doing is, again, I'm going to take an Stern-Gerlach experiment along the z direction. I'll get two beams, okay, and then I will block out the minus beam, and the plus beam I will again feed through a Stern-Gerlach experiment. So this is SGZ, this is plus Z, the minus Z beam is blocked, and the plus Z beam, this time I'm going to feed through another Stern-Gerlach experiment, but this time the magnets are going to be in the X direction, not along the Z direction. Okay. Now this can be a little interesting. So what does this give us? So remember that the first Stern-Gerlach experiment, in which I just pushed all these silver atoms through an experiment with inhomogeneous magnetic field along the Z direction, split my beam into two. 50% of the particles had plus h bar over 2 as the spin and the Z direction, and 50% of the particle had minus h bar over 2 as the spin value. Now I'm filtering out only one beam that has SZ value, SZ value plus h bar over 2. And now I'm trying to differentiate this beam according to the spin value in the X direction. If I do this experiment, it turns out that I get two beams again. Get a beam. Okay. But this time the beams are differentiated according to their SX values. So this corresponds to plus X, and this beam corresponds to minus X. In other words, this plus Z beam that probably has about 100 atoms or so is split into two beams, 50 atoms that have Sx equal to plus h bar over 2 and Sx equal to minus h bar. Okay. Now let us take stock of the experiments up till now. Okay. So yes, the first step, you understood that there is something wrong with the classical way of looking at things, because spin does not seem to have a continuous spectrum of values like you expect a spinning top will have. The spinning top can have an angle of L equal to I omega, L can be anything you want, right? Because omega can be anything you want. So an electron spin is not like a spinning top. That is what we understood from the first experiment, because there's only 2 beams and not an infinite number of beams. The first experiment told you that, okay, the plus Z beam with only SZ value plus h bar over 2 can, if you put another Stern-Gerlach experiment, it's going to give you the exact same thing. And this you do not find surprising, because you said that the parent beam that is going in, which is this guy, has only that value. So whatever goes out has to come out. So this beam should also have the same value of SZ. Okay, this was understandable to us, even if you are thinking about this classically. Okay, so now let us try to interpret experiment number 2 classically. Again, when I say classically, I know that classically is not the right way to interpret, but I'm trying to push the boundaries here. So yes, I have a parent beam that is SZ equal to plus h bar over 2. And now I seem to have differentiated this parent beam into 2 beams that have Sx equal to plus h bar over 2 and Sy equal to Sx equal to minus h bar over 2. So can I explain this classically? Well, you say that, yes, you might be able to. For example, 50% of the beams that have Sz equal to plus h bar over 2 also have Sx equal to plus h bar over 2. And 50% of the beams also have Sz equal to minus h bar over 2. Sorry, Sz equal to plus h bar over 2 and Sx equal to minus h bar over 2. Okay? In other words, you ascribe a statistical distribution of these atoms. You say that 50% of the atoms might have, let us call this roughly plus, we'll call it spin up, and minus, we will call it spin down. Okay, this is just a rough terminology. So we can try to explain experiment number 2 as follows. We will simply say that 50% of the atoms have spin up in the z direction and spin up in the x direction, and 50% of these atoms have spin up in the z direction and spin down in the x direction. What is the problem? Okay, this is a problem, but to understand what this problem is, we have to move forward. So let us consider a third variation of the exact same experiment. So we'll call, this is somehow not popping up. So I'll stop share and start sharing again. Just give me 1 second. Okay. So hopefully things are visible now. So experiment number 3, I will again start with the same setup. Okay, I'll bore you guys with a Stern-Gerlach experiment in the z direction. I will get a plus z beam and a minus z beam. Okay, and then I will block the minus z beam. And then the plus z beam, I will feed through a Stern-Gerlach experiment in the x direction. I will get a plus x beam and a minus x beam. Now I will block the minus x beam. Okay, so this is Stern-Gerlach experiment in the z direction. This is the plus z beam. This is the minus z beam. Okay, I've blocked the minus z beam. This is a Stern-Gerlach experiment in the x direction. Again, I get a plus x beam and a minus x beam, and I've blocked the minus x beam. Now I'll do something a little tricky. I will feed this plus x beam into a third Stern-Gerlach experiment. Again in the z direction. Okay. Now let us pause to understand what the classical physicist might expect at this stage. The classical physicist might think the following. Look, initially you split the atoms into 2 beams, or some of the beams had Sz equal to plus h bar over 2, and some of the atoms had Sz equal to minus h bar over 2, and you blocked all the atoms that have minus h bar over 2. So I am thinking that any atom that survives cannot possibly have Sz equal to minus h bar over 2, because all such atoms were blocked at this stage, right? They were blocked right at this stage. There is no way there can be any remaining atoms with Sz equal to plus h bar over 2. So if you ascribe a classical way of thinking about things, like you assume that this total atoms is a statistical mixture of atoms that are in the spin up state and the atoms in the spin down state, then the logical conclusion of the last experiment would be to say that you will only get one beam outside, because the plus x beam of atoms that is fed into the last stage of the Stern-Gerlach experiment does not have any spin z down component at all, because all such spin down components of the Sz are filtered out in the first stage. If you actually do this experiment, however, you find that again you get two beams. One that has Sz equal to plus h bar over 2 and Sz equal to minus h bar over 2. Okay. So this is the result of this thought experiment. So now we have to sit back and try to understand what is going on at this stage. So what's happening? A classical way of looking at things just does not help. It does not help simply because if you ascribe, so if you think of these silver atoms as being a bunch of balls, okay, and spin up is red and spin down is blue or something like that. And in the first stage, if I block out all the blue balls, and if I only do a series of experiments on red balls, there is no way at the end of the experiment I will get 10 blue balls and 10 red balls. That is simply not possible, right? So that is exactly the classical way of looking at it. Classical way of looking at it is simply saying that, look, initially I had, let us say, 100 atoms. 50 atoms were red, 50 atoms were blue. I filtered out all the blue atoms, okay? And they only fed the red atoms into subsequent experiments. And whatever I get, so let us call the plus x as something and minus x as some other attributes of the ball. But whatever I get at the end, I should only get the red color balls. I cannot possibly get the blue color balls. Yes? Okay. Oh, sorry. There is a bunch of questions that I missed, but I will address these questions as we go along. So I will get a whole bunch of red color balls and whole bunch of blue color balls. So the classical physicist would simply not agree that the last stage of the experiment would give me both red and blue color balls. But this is exactly what happens quantum mechanically. There is no way to refute this. There is no way to explain this using classical mechanics. You need a new way of understanding what the results of the measurement are. And you actually need a new way of understanding what measurement itself is. Okay. Now let me pause and look at some of your questions. If B is a vector, how can we take gradient of a vector field? Oh, okay, sorry. So that is a very, very good comment. So this is some B. This is actually the way you actually understand this is by saying this is del of mu dot, del of the force. So del of the potential. The potential is mu dot B. So I should actually write del of mu dot B, not mu dot del B. Del of mu dot B is not mu dot del B. Okay, thank you. Oops. The second question is same question as above. Yeah, Sachin, that was a typo in my notes. Why is it necessary that exactly half of atoms have plus value and half of atoms have minus value? This is something I will explain as we go along. Okay, so this is a very good question, but at this stage I will defer this question. Why then the same thing does not happen in first experiment? What is happening in first experiment? Okay, very good question. So the difference between the first experiment and the second experiment is that in the first experiment, so again, I think this is not sharing. Yeah, so there's something wrong with this sharing business going on. So I'll share it again. Okay. Okay. So I think this is now good. So in the first experiment, I am putting the Stern-Gerlach experiment in the Z direction, and I'm splitting the atoms into plus Z and minus Z, and I'm again putting the same Stern-Gerlach experiment in the Z direction. I am not changing the direction of the magnetic field gradient. Okay. Yes, Pankaj, we are going towards superposition. So hold on for a while. I'll explain. There's no point just saying terminology without telling what it actually means. So that is why I'm not using superposition right now. Yes, it is superposition. Very good. So this time, the second experiment, the first splits the beam according to the SZ value, and the second experiment splits the beam along the X value, not along the Z value. Okay. Now, if you compare experiment number 0 and experiment number 3, right? If none of the intermediate things were there, if you simply look at the very last stage of feeding some beam into SG in the Z direction, you get plus Z and minus Z, which is exactly what the experiment number 0 also tells you, right? But however, the introduction of the SG along the X direction somehow seems to conflict with our way of understanding things. So mathematically, the way to formulate this is something that I will get to in the subsequent lectures. Mathematically, we say that Sx and Sy are incompatible observables. They don't commute. But what literally this means is that the Stern-Gerlach experiment along the X direction somehow seems to hide or ruin the information about what happened before. So it simply doesn't matter what happened before. If you feed the last beam into these SGZ machine again, you again get two beams with SZ equal to plus H bar over 2 and SZ equal to minus H bar over 2. Exactly as you would get in experiment 0. Okay. So the middle part where something bizarre happens is when you introduce a Stern-Gerlach experiment in the X direction. Equivalently, the same thing would happen if you choose SGY direction in the middle, not the X direction. Okay. So what is happening here is a little crazy. So I cannot think of, let us say, suppose if I want to write down mathematically what these beams are, right? So I cannot write down, say, let us say the total number of beams, total number of atoms is n, and this is equal to some number of atoms with n plus and some number of atoms with n minus, where n plus is number of atoms with Sz equal to plus H bar over 2 and n minus is Sz equal to minus H bar over 2. Okay, I simply cannot understand. This is called a statistical mixture. Okay, a statistical mixture simply says that if you have 100 balls, 75 of which are red and 25 of which are blue, then the chances that you would get a red ball out of any random picking is 3/4, and the chances that you would get a blue ball are 1/4. That is a statistical mixture. This is not a statistical mixture of beams. So I cannot think of the electron beam as being composed of 75% of spin up in the Z direction and 25% of spin down in the Z direction. Because if I think of it that way, then I cannot explain experiment number 3. Okay, if I've blocked all the 25% of beams, 25% of the atoms with Sz equal to minus H bar over 2, there's no way I can again get it in I cannot regenerate things at the last stage, right? So it is a mixture, but it is not a statistical mixture. Okay, this mixture, as somebody pointed out already, is called a superposition. It's a superposition of states. Okay. So what is a superposition of states? Sorry, my connection keeps falling. I don't know why. This Bluetooth has a problem, probably. This is a superposition of states. So the way I have to write this is not by saying that the total number of atoms is, some number of atoms with this value and some number of atoms with that value, but I should actually write this as some state. Let us call this state I don't know, whatever state this is, some state alpha, okay, is some linear combination of some other states. So it is a linear superposition of some other states. So let us say A1 times some state beta 1 plus A2 times some state beta 2 plus A3 times some state beta 3 plus blah, blah. Okay. So the way I understand this is by saying that I can look upon the state plus Z as a linear combination of the states plus X and minus X. Okay. Now I have to interpret what this 1 over root 2 is. I will do that in the next class. I have to impress upon you that this is not a statistical mixture. Okay. So question is, does Maxwell-Boltzmann statistics fail here? So again, Maxwell-Boltzmann statistics is a classical statistics. Okay. So it doesn't take into account the intrinsic spin nature of objects, for which you have to have, bosonic or fermionic, so you have to have different statistics, but that is not quite what I mean here. So when I say statistical mixture, I simply mean that the way you assign probabilities is different. Okay, so in some sense, that is what the Maxwell-Boltzmann or Bose-Einstein or Fermi-Dirac distributions also are. They are weights to assign probabilities. The way you assign probability is slightly different. So in other words, I simply cannot say that the total number of atoms is 30 atoms in the plus direction and 70 atoms in the minus direction, so that probability of up is 3/10 and the probability of down is 7/10. That is not how I assign probability. So one should assign probabilities differently. Okay. Now, how one should assign probabilities is something that we will consider in detail in the next lecture, but this is what it is. So if I have a linear combination of states, first of all, if this linear combination is something that bothers you, notice that you have actually seen this before. So suppose if I write any vector in 3 dimensions, a vector has x component times I plus y component times j plus z component times k. This is exactly what you're doing, right? You are writing the A vector as a linear combination of I vector, j vector, and k vector, right? That is exactly what I'm doing here, albeit in a very funny notation. That is exactly what this means too. I'm not putting an arrow over the plus z. I'm simply enclosing it in very strange brackets. But in a sense, that is what I'm doing. In fact, I will be using or appealing to your intuition about vector algebra to develop the concept of linear vector space in the next week. But essentially, that is what I'm doing. But of course, I have to understand it is not, understand these weights of 1 over root 2 here and 1 over root 2 here, and how these weights are connected to the probabilities. That we will cover in the next lecture as we go along. But essentially, the goal of the upshot of today's lecture is as follows. Suppose if you have observations, you can have certain observations that are not compatible with each other. In this particular case, the measurement of spin along the x direction has somehow has somehow ruined all the past history, right? So feeding the plus x beam in the z direction experiment simply gives you exactly the same thing as you would have gotten in the very first experiment number 0, right? So there is something really funny going on when you, but the same thing doesn't happen if you do it in experiment number 1. Suppose if I put another, at the end of this plus z, if I put another sg in the z hat, I'm again going to get only plus z. I can keep doing this indefinitely. I will only get plus z. Okay. So the result of the experiment number 1 is clear because I'm blocking out minus z. And if I measure z again, I'm only going to get plus z. If I measure z again, I'm only going to get plus z. But if I change the experiment slightly by measuring x in the middle and then measuring z again, I get something radically different. Okay. If I measure x and then I measure z, I get something radically different. I get both the possible values. Okay. So this is the essential difference between classical and quantum mechanics. There is something very interesting or strange going on when you deal with observations of two different kinds of measurements. Two measurements can be compatible with each other, so I don't find this strangeness. An example is measuring the same thing over and over again as an experiment number one, or two measurements need not be compatible with each other, in which case your classical intuition fails, an example of which is experiment number 3. Okay, so that is basically what I wanted to convey to you. This is a good place to stop for today because I don't want to go on and start something that I cannot finish in the next 4 minutes or so. So in the next lecture, I will talk a little bit more about this superposition and what this equation means in more detail. Okay, and then I will try to explain this a little bit more mathematically by making a connection with the usual notion of vector algebra that you have already learned in your BSc. So the next 4 minutes, is there any questions? In experiment number 1, instead of feeding the beam through SG plus, again, if I feed the beam through SG minus Z, in experiment number 1, so again, I am not feeding the beam through SG plus Z or minus G. I am simply feeding it through an experiment in the Z direction. Okay. So if I feed the plus Z beam through a Stern-Gerlach experiment in the Z direction, I will only get the plus Z beam back again in experiment number 1. If I feed it through a Stern-Gerlach experiment in the X direction, like I do in experiment number 2, I get two beams, one with Sx equal to plus h bar over 2 and one with Sx equal to minus h bar over 2. So the experiment itself is designed to split the beams into two, one with spin plus h bar over 2 and one with spin minus h bar over 2 in whatever direction you want. The direction you choose by aligning the magnets along the Z direction, Y direction, X direction. Okay. So I am not aligning the magnets and I'm not creating something in the plus Z direction alone. I am creating inhomogeneity along the Z direction. And creating the inhomogeneous magnetic field along the Z direction will help me split the beam into plus Z or minus Z. Amit, if we feed in minus C in experiment, so that is exactly what I explained just now. So hopefully that is clear to you also. Any other questions?